All right,
It's all yours.
got it. Welcome everyone to the last meeting of the year for the Joint Club Robotics meeting group. Today, my name is Jim D'Annunzio, and we have a special guest this this time, Scott Horton, who will be showing his robot, the ElsaBot, and all of its cool features. It was an entry into the Open CVAI competition this year, which I also had an entry, and I've been following it as well, and corresponding with Scott about it. And it's quite cool, and we'll get to him and after announcements and in our business meeting that should be pretty quick. So first, I guess it's combination business and announcements. If you didn't notice, or if you're not on our mailing list, we now have the RSSC club has published the ability to donate to the RSSC, donate cash to the RSSC via the internet now, or via PayPal. And so we encourage anybody who can give to the RSSC for the optional $10 membership, or any amount that you feel that you can afford. We appreciate anything you can give, and that is on our main webpage, rssc.org. And yes, we will be skipping December 25th, would normally be our next meeting, and rather than have an alternate date, I think the rest of December, most people are going to be busy. So we'll meet again in January after this.
Yeah, good job on the PayPal. As they say in Travelers, a time travel series on Netflix. Welcome to the 21st. Good job.
Yeah, I'm getting Ron to try to link the bank account, but that's just the last thing. And also, yeah, you probably saw I worked on an apparel or logo store for RSSC, and we have a link to that, so you can get shirts and coffee mugs with our happy robot, our IdeaBot. And I don't know if anybody's tried to order from them yet, but I may try it myself to see how, make sure the product is good.
Like that, keep a lot of robotics shirts. Jim, when we get to the announcements, I have an announcement.
Oh yeah, yes. Why don't you go ahead?
All right, the Riverside Robotics Society is meeting in person next Saturday, a week from tomorrow. We're going to have our robot dance contest. So bring your robots. We have prizes. We're going to be awarding lots of prizes. Autonomous robots will have a separate category, separate from remote control robots, but all will have a chance to dance. So that'll be a lot of fun. That's 10 a.m. here in Riverside. I'll post it to the mailing list.
So that is next Saturday.
Yeah, a week from tomorrow.
Okay. If I get a ride with Alan, I'll be there.
All right. That's it, Jim.
All right. Let me just, I'm going to post the donate link in here, and also the link for
Mobile wrap.
the store. Let's see. Where is it? There it is. So those are the two. I pasted them in there. And yeah, check it out. So any other, oh, I guess, I know we bring up this every time, but just to check on the university status from Alan. Could be in next few months, we might have our in-person location available again.
Yeah, for sure. There's a couple of factors. The campus has been allowing third-party meetings and club stuff on campus, which is a great sign. Our sponsor, Walter, has indicated that we may be able to continue our in-person meetings for Long Beach in as soon as January.
Oh,
So that's something
excellent.
he's working through right now.
Oh,
So
that'd be
after the
cool.
holidays, we'll, continue to work through that. And if everything, as long as things don't get any worse and continue to get better, I'm looking forward to meeting up with everyone in person in January.
Okay, great. Yeah, because I think I talked to Walter and he said, yeah, he referred me to you as well. So, but great, that's good news. Excellent news. And then, yeah, Riverside has already started meeting again, which is good. I've been to one so far. And that's great that we're start to do that again. Seriously looking forward to it. And there may be people that we haven't seen in a long time will be showing up, perhaps, but we'll announce as soon as I find out. It'll go into the mailing list. And oh, the other announcement is next month is January. We, according to our bylaws, we are going to elect the officers for 2022 of RSSC. This is RSSC specific stuff. Pardon me, pardon to the other clubs. So just to announce that I'm not planning to run for 2022. So please keep that in mind. And if anyone who's interested in working as an officer, and I know Ben Partisi has done it several times, and he may run again. We'll have to ask him. Some of the other, but it's of course something to think about if you would like to play a role. We have the secretary and the treasurer, probably Ron, but if there's someone else interested, I don't know. And then we have the vice president and president. So, and then, yeah, and all of them are on the board. So, and we can, I think, have additional board members, but so that's, we'll do that in early January. And I think that's it. Anything else from announcements?
I wanted to mention that I put the link up. They have discovered a warp bubble. DARPA did. So I know there's a lot of Star Trek guys on here. So they,
I see.
in that they actually have proven that it can be done.
A warp bubble.
So
We'll have to read about that to know what part of physics that's really talking about.
not really robotics related, but I know there's a lot of people who might be interested in that. To me, it just seems neat that I've lived long enough to go from flying on propeller-driven aircraft to see a warp bubble generated.
Oh, I see. They actually created one, huh? All right, cool. Well, I guess I think that's it. Yeah, that is it for me. And
I have a question about
Oh.
that warp bubble. You're saying they've actually created warp drive, or
Now
are they redefining it? What? Because like that's huge.
they were running a different experiment and they created a warp bubble. The math proved that it actually created the warp in time and space.
So it actually folds time and space upon itself to move an object from one point to another.
That's what it looks like. So
Holy
Is that what this,
that's not good.
is that what Star Trek actually was? I don't know. I don't know what the fictional version versus the reality has anything to do with each other, but well,
Well, the fictional logic behind warp drive is if you take a piece of paper, draw a dot on it, and then fold that paper in half,
yeah.
and that dot moves from where it was in that space to the other side of the paper. When you open the paper back up and open it up, it's jumped that space.
Yep.
That's warp drive,
All right, but you're warping,
time and space.
you're potentially warping hundreds of light years of, anyway, whatever.
Yeah, that's crazy.
Surprise.
All right, well, we can get to that in show and tell later, but now without further ado, I think it's time to begin our main feature event. And Scott Horton will be presenting his Elsa bot, and please take it away, Scott.
Okay, well, thanks for the intro. I'm glad to be here, and hopefully I can share something interesting from what I've been working on over the last. Well, actually, I haven't been working on it that much, but first of the year there was a lot of work, so hopefully you'll get an idea about that. Let me share my screen here if I can do that. Let's see. Okay, can you see that? Okay, I should see the browser there with the Elsa bot.
up there.
Okay, so I'm going to just kind of walk you through. I've got just a little bit of a outline here, and then I'm going to kind of bounce around some documents. I also have Elsa bot here watching right now, and also there's Elsa bot there. She's running a very simple behavior tree right now, but she's with us right now, so we'll just kind of park her to the corner there. But yeah, so the robot was really a continuation of another project I was doing about this time last year, where I was also using the iRobot Create 2 base for the robot, but I was using a Jetson Nano and a RealSense camera. And for that, it was just a little bit of just a ball picker type application where use the Nano to detect the ball using object detection, and then based on the position, using a RealSense depth camera, go to it and then get the robot where it needed to be, so a simple arm could pick up the ball and drop it in a hopper. And so that was kind of last year's challenge, and that was a lot of fun. And then also this project, I wanted to use the new OD camera that was just, I don't know if they were available about now or they were coming in right now. It seemed like about last year this time. And then my other motivation was just to somehow involve my 3-year-old granddaughter, if anything, to wow her, to amaze her, or whatever, just to maybe spark some interest, maybe in her down the road, and maybe more projects down the road. So that was kind of what got me going on it. This slide, I've just got a bunch of links. Mostly everything, all the stuff for this project is on my GitHub account, and a few noteworthy repos up there are listed here. And the first one is really just a top level that contains the project report that I did for the competition. And that's just how I published it by this repo. And we'll be looking at it a little bit. But that's, if you care to get a little deeper, that's the thing, that's the document to go to. And the appendix actually lists all the other repos that are part of this project. And namely, it includes these right here, which these are the more noteworthy ones, which include the one for the robot head functionality, which is where the vision and the tracking, the servo tracking is implemented. And we'll talk about all about this a little bit later. The main control portion of it, where behavior trees are implemented and used, and then some of the speech processing, which is pretty much old hat these days, but there's just yet another implementation. And then of course there's some other repos, but if you have any questions, if you just want to interrupt me anytime, that's cool. But if not, I'll just keep blasting away here. So let me open up or pull up this document, this report, and we'll use it a little bit. And so let's kind of cover the platform of the robot, and maybe go back to this top level picture. And as you can see, there's a Create 2 base that's pretty much an off-the-shelf base, and on it I have an acrylic plate that I have mounted onto it, and then onto that is extrusion. I'm using 20 millimeter square extrusion just to create a frame up and around and one piece across, and on that I've 3D printed some lightweight sections that basically encapsulate the sides, and there's a real thin piece of, I think it's about 1.5 millimeter ABS that I just ordered off Amazon that I cut a hole in for the display, and it just wraps around. And so these side pieces actually have a slot in them that holds that piece in place. And so that's the look of it, but you'll see that there's also then portions down below, and we'll talk about that in a minute. And of course the camera or the head unit is mounted on a servo assembly that we'll talk about in just a second. And if we look closer, maybe look at the base a little bit, work up. There's a LiDAR mounted on the front, and it's an RP LiDAR A1. And
Scott,
yes,
your image is not centered in the screen. Your PowerPoint presentation's all skewed to the, yeah, that's better.
can you see that?
Yeah,
Okay,
that's better.
all right. So, all right, thank you.
I just want to make sure I can see the whole thing.
Yeah.
If they're displaying it, we're seeing your view and not the display view, not the present. We're seeing the presenter's view, not the audience view.
Let's see, can I see what I'm seeing somewhere? Is there a way for me to preview my my screen, or?
Are you using PowerPoint?
Well, I've just got my desktop. So what am I sharing? Are you seeing my desktop?
Yeah,
Yes, we're seeing your desktop.
That's what you should see right now.
All right, good.
Yeah, I'm showing you my the PDF document for the report for the project. And so you should see 4 images right there right now, the head view, and then some others. Is that right?
Yeah, it's good. It's good.
Okay, good. All right. So yeah, in this lower right image, you can see there's the LiDAR, and then there's a mic array mounted above it, and then there's a USB speaker behind it. And then over to the, let's just go up to the upper left, you'll see the head assembly, and there's the 3 holes where the 3 cameras of the Oak D peer out. And you can see on this picture to the right where the Oak D is mounted up against that plate. And you can see the servos that are back there. And then of course under that is just a little homemade kind of mouth talking indicator, smile indicator, whatever you want to call it, that's just used just to provide feedback. And those lights will kind of do a little random pattern when she's talking, or they'll produce a smile just for reactions. And then of course LEDs just blink a pattern just as another way to provide feedback. And this head is mounted on 3 servos, a pan and tilt and a rotate axis. The pan and tilt are the most important. The rotate just tilts the head, side to side, just more for effect, just for more of a kind of an emotional thing, but the servos allow it then to track, and we'll talk about that a little bit more. And then inside, there's a display panel there, just an off-the-shelf 1024 by 600 resolution panel. And I ended up with 2 Raspberry Pis. I started out with 1, and we'll talk about why 2 in a moment. And there's also just a little board with some DC to DC converters. I'm using a Ryobi 18-volt battery. It's a 4 amp hour, and which works out well. I already had them, use them for my yard stuff and drill. And so it's just sort of a natural fit to use that since I've got chargers and batteries. And they've got a powered USB hub. And so that's really the bulk of the hardware. So that's the platform. Any questions on any of that, or if not, I'll keep going. So let's see.
I had a question. Which mic array? Are you using that common circular one that I've seen out with like 7 or 8 mics or something like that?
Yeah, it's something like that. It's a brand is Seed, the SEED brand.
Yeah.
And it works pretty good. It'll give you an angle of arrival and voice detection indications, and you can control the light colors a little bit just to, have a little bit control over that. So I found it to work pretty good. It was cheap enough. All this stuff is really cheap these days as compared to what it could be. So it's just really amazing what you can get in a small package now.
Great.
Okay, I'm going to go ahead and show you at least some of this video. So this is the video I submitted for the competition, and it's just going to show you the things that the actual behaviors that ended up being used for this project. And I've got it muted. This part right here, let me just kind of skip on this. She's just kind of describing what I just told you for the most part about why she exists. So I can move on. There we go. And so she can play 3 different games. And so one of them is kind of a classic hide and seek where the robot's the seeker. And there's another game where the robot tells the child to pose in a certain way, hand up, out, whatever. And the robot detects that, and that type of game. And then there's a find where it's not really the robot finding, but it's telling the child to find a certain object on the floor. And so those are the 3 games. And so we'll just kind of flow into.
The first is robot hide and seek. Hi there, Caroline. Hi.
I'm gonna pause it here just to kind of give you the framework here. So obviously the view up here in the center, top center, is the camera, is the robot's view, and the robot or the view, there's annotation showing where a human is detected, since it's using that type of detector, or at least it cares about that type of object with the detector. And it's also running a human pose detection, and so it's showing the skeletal outline there. And let's see. And so the game starts out by, you want to play this game or this game or this game, and you basically answer yes, and then it goes down that path.
Would you like to play again? Yes. Okay. Do you want to play robot hide and seek? Yes. Yay! Great. Let's play.
Yeah, and by this time she was so tired of doing this. There were too many takes, and so it was amazing that she was able to be cooperative enough to do this. So she was really done at this point, to be honest, but she was a trooper. But right now at this point, so it's going to start, and so this new image or this new window that shows up is actually a view from a web view of the robot's web interface, and it's showing a very cleaned up map that I made, from the mapping. And in this map, it's actually, if you can see, there's some numbers, and those are designated search locations that are specified using a JSON file that have the map coordinates. And then this gray dot here is the robot location, and the blue dot is my daughter and granddaughter sitting right there. And so that's the map, and you'll see now.
Hold on while I get ready.
And so getting ready means that she is calculating from her location, she's calculating a path to each of these points to determine the best point to start searching first based on where she is. And then she'll just take a always constant sequence around the numbers.
Let's play. I'll count to 10 while you go on hide.
And all this is behavior tree programming, just, it's pretty straightforward.
4, 5, 6, 7, 8, 9, 10.
This is the
Great. Now here I come, Caroline.
it's the free too.
So Scott, you're saying during that pause, she calculated like a sort of traveling salesman type, or
She just calculated a path to each of the 5 locations.
from
And-
where she is now, you mean?
Yeah, from where she was, and then just calculated the distance of those paths, and so she would end up taking the shortest. There's a little more complication in the code where it would factor in the angle or the direction she's pointing, but in the simplest case, it's pretty much the closest point. And so now she's going to that number 1 point, because that was the closest point that she calculated. And so let's see. And then of course she got her view down in the lower left corner now. And at each point you can specify whether she pans her head back and forth once, or whether she just does a quick look and then continues going. So there's some dimensions to how she searches as well. And then also when she's moving, question, you can enable it to scan back and forth.
I'm still looking for you, Caroline. For this game, I use ROS2 and the nav2 navigation stack to search the room for my friend. While moving, I use a MobileNet SSD version 2 neural network running on the LC to look for my friend. I'm still looking for you, Caroline.
So you can see there she is in the map up there, and that's her next path. And I forgot to put the video inset back, so sorry about that. It would have been better.
Would you like to play again? The next
That was a pretty straightforward game because it just kind of goes through the spots just looking for somebody, and obviously it doesn't know who it's looking for. If it finds anybody, then it declares victory. So any questions on that game? Okay.
next game I will show is called Robot Fed. Here's how to play Robot Fed. I'll tell you where to put your hand.
And that's my grandson in the background narrating things as best as he can.
If you want to stop, just inhale the box. Put your arms to your side. Nice going. Stretch your arms.
And so you'll see up in the upper
For
left
this
corner,
game, I use a media pipe pose, human pose detection neural network to recognize the hand and arm position.
and so it displays, it annotates what it's actually detecting in the upper left corner. And that's basically post-processing after the actual media pipe lays pose detection. And so those are calculations based on the arm, the joint positions, the shoulder and the elbows. So it's really pretty simple. Just looking at ranges of angles to map those to particular poses such as arm above, or arm to side or touching shoulder, etc.
Put your right hand high above your head.
So you had to determine the angles for each of those
That's right.
modes, right? Yeah.
Yeah, it's almost like a big switch statement for the most part, something to that effect. It's really not very complicated. It's like, well, if it's down a certain degree or less, then et cetera. And so wasn't too much magic. And I chose some that were easier to discern, especially with a child that's not going to be very precise, and you want to be forgiving anyway. And so but mostly worked for her.
The next game I will show is called Robot Find.
And this one's kind of interesting because it brings in a lot of, the ROS mapping capabilities and the robot depth perception and quite a few elements. And I'll talk a little bit about that more in a second.
For this game, I use the MobileNet SSD neural network to detect the player and use the depth measurement capabilities of OC to measure the distance to the player.
So I'll narrate it from here. So yeah, the gist of it is the robot knows where she is on the map. She knows where these cards have been placed. There's a calibration step in the game where you can go through and tell it, from 1 through, it supports 9 cards, but for each card, you raise your hand up and you basically say a card is here. And so, she remembers that. And then of course you can put any kind of card you want. The game allows you just to tell it what it is that, the type of card you have in place. It could be letters or numbers as well. But then now that the robot knows where those cards are relative to the floor map, then it's all about, well, at any given time, the robot can, determine what angle, where robot is, the angle it's facing, the angle of the pan and tilt to actually point to the person, and then the distance. And then that's all you need to then transform all that into a map location to then correlate that to a well-known location. So it just kind of, it's not rocket science or anything, but it's kind of fun being able to put all those different things together to do, you know, something kind of amusing, I guess. So that was basically what the robot, that was at least the portions of the capabilities of the robot that were actually, you know, used for the games. And so let's talk about a little bit about the software architecture now. And let's see, I've got a diagram for that. So this is all ROS based. And so with ROS, you know, it's sort of a distributed architecture. And so, you know, the functionality is implemented using packages which are executed as nodes in the system. And so this diagram is depicting the key nodes. You've got the garden variety nodes that are off the shelf, like the ROS2 Nav2 related nodes, the Create2 driver base node, and the RP LiDAR. All that stuff is kind of depicted down here, which really no need to go into details on that. That's pretty common stuff. Up here, this area is the custom nodes. The middle portion relates to the behavior tree, the control portion of the firmware of the software. And we'll come back to that in a second. And these areas around it are other nodes that are going to feed in either status information or receive control from the control nodes. Of course, the point of this project really was more of AI vision. And so this vision node is the node that captures that functionality. And this is the node where the neural nets run. It's the one that's controlling the OD and receiving detection and calculating detections. And then that data that it determines, the detections feed into a tracker node, which uses the detection information to control the servos to keep the person in view, as well as it can control the base to keep the base of the robot facing the person, and then, you know, the head further tracking. And then there's a viewer node that just displays the camera on the local display. Then off to the right, there's some speech processing nodes, synthesis and speech recognition, as well as wake word detection. And these are making use of the Microsoft Azure speech services. And I went with Microsoft since they were a sponsor of the competition. You know, obviously probably would have used AWS, but anyway, these worked well. It's kind of weird using Microsoft stuff on a Linux-based device, but whatever. And then the middle section, of course, is control. And so it's based on the behavior tree CPP library, which ROS2 uses as part of the nav stack. So it's already linked in, or already there to be used to link in. And so the way that works is that it basically is, you create these behavior trees in XML format, and it's a collection of nodes, tree nodes, and the leaf nodes are sort of called action nodes. And those are the things that typically interact with your system. And so you can have nodes, action nodes that maybe receive information from some portion of the system, as well as make a control action out to a node. And all the fun stuff, I think, was really kind of, a lot of it was in these nodes, you know, creating these to allow a tree action to interact with the rest of the system. And we'll go into more detail on that. But the key thing is that once you have all this in place and you have these nodes that allow you to interact with, let's say, speech or vision or controlling the head or some of the feedback elements, it's all about these XML files you create as far as how you make use of those elements. And so in theory, anybody could write an XML file. It's just a text file. So if you know how these elements function, you know, how you make the behavior work is all in this very high level description. So which is kind of nice. It's a different way to describe functionality, but definitely can get the job done. You'll notice there's a blue and a green box. The blue, turns out when I started integrating this functionality, this overall functionality, I realized that the nav2 functionality was taking close to 70% of the Raspberry Pi 4 CPU. And, that was kind of a problem since we couldn't use that much. I needed more, I needed enough to run the rest of this. So the beauty of ROS is it's distributed in nature. So I just dropped another Pi 4 on there and put all the more of the base layer kinds of nodes on that, and then ran everything else on a 4 on another 4, and kind of moved on. And so wasn't too big of a deal at that point. So
Hey, Scott, you might want to maximize your windows.
is this a little bit too tiny for you?
Well, just to, for people that different
Okay.
screens.
Okay, yeah, let me see if I can choose a better one here. Yeah, I wasn't too sure how this higher res screen was gonna do. It's a little bit more than 1080 p, but anyway, can everybody see this diagram okay? And does anybody have any questions on this portion of it?
Oh, I had a question. Did you write most of these nodes are in the new Python, ROS 2 Python, or is it ROS 2, is it C++?
Yeah, that's a good question. Everything, well, the only Python are these two, or well, these 3 nodes here, and everything else is C++.
Well, your cursor isn't showing up. Is this cursor showing up for anybody?
No,
Is there a way to make that happen? Because I've been trying to point and thinking that you were seeing my pointer.
It's supposed to happen, actually.
Really?
When you share the screen, it should just show up. Is this,
Might want to cancel sharing and restart it or something, or just.
Okay, all right.
is this available online, Scott?
Yes, all these documents are going to be available. So you can drill into those and, at your will and kind of see the details. Is that any better now? No.
There's
Okay, that's too bad. So the vision and the tracker and the viewer node, just to put it in words, those are Python, and everything else is C++. And the reason I use Python, because originally I thought, well, I'll just do it in all C++. I learned real quickly, it's just a lot easier to deal with this AI stuff, the first level of it in Python, because first of all, OD stuff seemed to be initially more Python, supported. And then, when you start talking about, all the, NumPy, or just the kinds of things we talk about, tensors and, all those things that have to be post-processed that come out of these neural net devices. It's just, Python is just just a lot easier. And then of course, then from there you can use ROS to send messages that, doesn't matter. It's agnostic at that point. You can go to any kind of node and implement it in any kind of language. Okay.
you said the nav portion was what was taking up all the computer time?
The nav2 processing. So all the, the localization, processing of the LiDAR inputs, and just the idling. Not when it was navigating per se, but just idling. It just seemed to take a lot of CPU. Maybe that was something along the way. Maybe it's been improved, but I haven't gone back to really assess that at this point. But in fact, I've actually moved on to a different single board computer. I switched to a Celeron based, and we'll talk about that a little bit later if we have time. Yeah, so. Okay.
Celeron's about a little more than twice as fast as the Raspberry.
I'm sorry?
The Celerons are a little more than twice as fast as the Raspberry Pis.
Yeah, and there's some other advantages too that I kind of like. The fact that they're x86 kind of makes things a little simpler, life a little easier in some cases. And but I'll tell you about the one I decided to go with in just a bit here. Okay, there's architecture, and then I was going to just kind of take a couple of topics, especially the vision and then the behavior tree portion, and drill into that a little bit. The other stuff hopefully is pretty straightforward. But the vision node is that vision.py module or I guess I just call it vision over in the other diagram. And I'm going to see if I can, I'm not sure if you'll be able to see this very well. I don't know if this is going to be too small. Can you make out this at all, or is it too small?
No,
Yeah, I can read. You can read it. You could try and
Yeah, go ahead and maximize the screen, and the keyboard shortcut under code is Control Shift and Plus will actually magnify the contents.
Oh, okay. Yeah. I knew there was, but I didn't know it offhand. So thank you very much.
My pleasure.
Yeah, so let's just take one of these or a few of these. So Vision PY is the top level, or is the node, and let me go down to the bottom for handling or setting up the actual AI, the OD device, and you'll see that this sets up just a typical ROS Python type node with this RCL PY init, and then we'll just go up to definition of this guy. And so for this class, it pretty much just does the init and stays in there. There's a loop. If you're familiar with ROS, there's a point where, you know, it does need to, let me show you here. It needs to come up for air and do a spin just so that it can receive messages and such. But for the most part, this function gets executed, this method gets executed, and then and all the magic just happens in its while loop. So, you know, with ROS, there's publishers and subscribers. And so this guy's of course, sets up a publisher to publish out what the detected objects are that it has found, as well as the pose detections. And then it receives, it subscribes to a few topics. One of the most important is just an enable, and another is feedback back to the node as to which particular object has been chosen to be the one that, you know, the system cares about, and talk about that a little bit later. But moving on down, there's a method called create pipeline. And if we look at that, which is down below a bit in the same file, this is where all the setup happens for the OD. And if you're familiar with OD at all, and let me get my browser back, you'll see that they've got pretty good documentation these days. And if you look at the depth AI documentation, they go into, you know, they talk about the pipeline, the device pipeline, and then they talk about various nodes that are available. And these are the functional nodes that are implemented by the camera, such as the camera function itself, and then different detection nodes. And there's image manipulation, which are like image scalers, and they can do other things. But these are kind of the building blocks that the camera system provides you. And so if you go back over to the code, you'll see where it's going through a sequence of just creating these different node types, these OD node types, and then connecting them up. So it's like a filter graph type of approach. So just for example, it's creating left and right cameras and setting the resolution, the frame rate, and then connecting those into a stereo depth node, which is the node that calculates depth by disparity calculation. And of course, that's going to feed in to another node down below. First, it creates a color camera node and sets its resolution and its frame rate. And if you go down below a little further, you'll see it creates an image manipulation node. And let me show you this first. Let me show you the big picture first. I should have done this before. This is a block diagram showing what's actually being set up. And this is the actual configuration of the OD for this application. And so as I was already showing you, there's a left and right monochrome camera that are set up, and it feeds into a stereo depth node, which is doing the calculation. And there's the color camera node on the left. And next to that is an image manipulation node, which resizes to 300 by 300, which feeds into the MobileNet spatial detection network, which also receives the depth information, which then feeds into an object tracker. So that sequence of camera nodes are set up to do the human detection part. I mean, it detects other things, but the application just cares about detecting a human.
So So you're doing this in OpenCV on the Raspberry Pi rather than using the functions that are available in the OAK-D?
No, these are actually OAK-D functionalities depicted here. Yeah, so there's Python. There's a Python API that, and then let me flip back over now. Go back over the code. So you'll see these different like pipeline create color camera. So that's an OAK-D specific API. They call it Depth AI, and so these are these are actually creating a configuration that's then going to actually get implemented on the actual board. And so yeah, that, yes.
When you say nodes here, are we talking about like an OpenCV node or node in the general sense, or are these actually ROS nodes?
Yeah, so yeah, this gets confusing because there's actually 3 different node types at play here right now. And let me go back. So this is the Depth AI documentation for the OAK-D, that's Luxonis website. And so, for example, this is their architecture. So here's the device, and they're kind of showing an example, just simplified. So what they would call a node here is like the color camera node, which this is basically an abstraction for the functionality that the camera hardware provides inside that device.
So would this be a Depth AI node?
Yes. So these are Depth AI nodes. If you look at this list here, these are the nodes that are implemented by the camera, the functionality of the camera. So that had nothing to do with ROS in this context. And so hopefully that's a little more clear.
Yes, that helps a lot.
Okay, good. Yeah, and so this is really all it's doing is using the Depth AI to create a pipeline of my choosing to do what I want it to do. And this is highly configurable. There's certain things you can't change. Like you've got to give, like this neural net needs 300 by 300. So you have to size the image to feed that into the neural net for it to work properly. There's a case right above it where I have an option to use tiny YOLO V4. And in that scenario, it needs a different resolution. So it's sized differently there, but it's this path else that it's taken normally. So just in a nutshell, you can kind of keep walking through this and you can just see where it creates a node, and then it connects inputs to it. And then that node is then connected to something else. And ultimately, we're creating a pipeline, and if you go back over to the PDF, you'll see that ultimately everything goes from this OAK-D device side in blue over to the Raspberry Pi 4 side, which is the Python implementation, the vision node. And so you've got these outputs. So this is an output from this object tracker node, which is essentially a list of objects that have been detected and that are being tracked. In other words, there's a common filter function in this object tracker node where it's trying to, between updates, trying to keep track of which is still there or which might be new. Then there's another path into the Raspberry Pi 4 side, the second line there, which is just the image, and that's just used to largely to publish to the other nodes. So that's the path there. And then this lower section is doing the human pose recognition, and it's actually more complicated because it's a 2-stage detection. There's a first neural net. It's a person detection that happens first, and it's just generally defining the person as a whole, where they are in the image or persons. And then the list of those detections are actually then post-processed on the Raspberry 4 side. And then the one you care about determining where the human pose elements, the joint points are, you send that image back to another neural net called a landmark detection neural net. And from that one, it then seeks to detect the actual joint locations in the image, and then feed that back as the LM detect path back to the Raspberry Pi 4, which is post-processed still a little bit more. So that particular case is a whole lot more complicated than the simple detection type networks, which pretty much say, here's a bounding box for it. And in the case of the Depth AI camera, it also tells you, here's your XYZ for it relative to the camera. confidence factor and the classification type. So, it depends on the neural net you're running. Some of them are pretty complicated, and this Blaze pose processing is something, that one of the other users of the OD had ported. They took the media pipe implementation and ported it to the OD, and so it was a great help that person did for everybody else. Let's see. So yeah, back over to the code. So, once you finish this pipeline setup, you've got all of those OD nodes configured and hooked up, and they're pretty much ready to go. And so if we go back up to the main method, one back up, and you'll see where it creates it, and then once it's created successfully, it starts it. So then it says run this pipeline, and so that's when the camera starts capturing frames and feeding those to the next stage down, the next node, and then this side, the Raspberry Pi side, creates cues, which are going to then be or it gets cues, which are going to then be used to receive whatever it is, if it's a frame or the actual neural net detection output. So each of these cues then are going to be used in this while loop. And so in a nutshell, it's going to say, hey, do I have a frame from the camera? Do I have any detections from that top path? And if not, just keep waiting. If I do, then it's going to go through and it's going to publish them. This published detections is a ROS publish, so it's going to publish those to any other node, ROS node that might care about them, and then it's going to also it's going to publish the frame. It's going to get the frame, and a little bit further down here, it's going to publish it. It's going to do the media pose, the Blaze pose, media pipe Blaze pose processing, and like I mentioned, it has to receive that first detection, do a little post processing on that, and then send that back to the neural net. So in data, let's see, set layer, and then it sends it. Here's the send where it's sending it back over into that second neural net, this one right here. So the send is representing that, and then from that, it gets back out then any inference results that it could find or produce. And then there's a bit of post-processing by the specific Blaze pose library, and then my function analyze pose goes in and says, okay, now that I know where all the joints are, let's see if I can figure out anything useful, such as, is the hand on the head, or is it touching the shoulder, et cetera. And that's what this is right here. These would be this would essentially be a left and a right result if there's anything detected. And of course that's published right here. So
Hey, Scott.
Yeah.
From your diagram, it looked like there was that there were things being published over to the other, or well, this is the OAK-D to the RPi. Oh, I see. When you're in this case, going from the blue to the green, really, it could just be another line of code in this just not on the OAK-D device itself. Like it's off the device. The code you showed us was connecting both of those to, is doing both green and blue.
Yeah, well, it's running on the green side, but it's these lines that cross from blue to green. There's calls like read the queue. Well, then of course that's pulling something from the blue side to the green side. There's also a send command where you're doing that send back over to process that landmark detection. So yeah, it's pretty much pulling stuff in and doing some crunching, and then maybe sending stuff back over as for the lower half, especially. The top part, object tracker, is pretty straightforward, since it's, once you get that result, you got it.
But yeah, you had to do that Blaze pose post-processing. That is a few calls to manipulate the data and then send it back to the neural net, other net.
Yeah, in part, and I created a little bit more complexity because in handling the Blaze pose, it could detect multiple people in the image, and I didn't want it to try to actually do the pose detection for anybody, for everybody. I wanted it to be just one person. And so in the tracker, in the tracker node, which we can look at in just a second, it gets a list of all of the detections. And from that, it tries to say, well, I care about the closest one and the closest person. If I haven't latched onto anybody, I'm going to go with the closest person. And then at that point, I'm going to try to stick with that person as long as that person is still tracked. And if not, then I'll go with somebody else. So that decision of who it tracks is fed back over to this particular node. And in this block right here, I believe this is where it's trying to correlate that, top level selection of a human to this particular, to this first stage of detection, where it's trying to detect a person too. And so it's trying to marry those up and say, okay, well, this is the person that corresponds to my overall detection. Therefore, let's get the human pose info for that person. And so that's really what's going on here. If it weren't for that, it would be a lot more straightforward. You could just send all the first level detections over and just show all the different poses. But I think I might have read though that it might not handle as well multiple people in the same frame. It might, some of these neural nets aren't as good at basically correlating the joints with individual people. It might get confused and you might end up with kind of poor detections. But so after each pass, it's pretty much gone in and it's, it has received a frame from the camera, and down below here, it will have annotated it. So it will have displayed all of the tracklets, which come from the tracker, showing the bounding boxes, at least the ones we care about. And then it will also have shown the, somewhere down here, it's going to show the human pose. If I must have missed that already. There's a function that overlays that. Here it is, blaze pose, landmark render. So that's where it's doing the skeleton draw. And then after it does that, it actually is, it's also overlaying the upper left corner, the detections as far as the interpreted pose detections. And then it's going to do a ROS publish right here. So converting the CV format to a ROS image type and then doing a publish right here. And so then, that gets fed to that local display as well as over to the web-based display, which is what I usually use to monitor it off the device. So
that brings up one other question about sending images across the ROS network. The camp, I think, has a lot of experience with. But did you have any networking issues sending images every video frames over?
Yeah. You definitely have to be careful because part of the reason the resolution is what it is what was 640 by 360 partly was for that, just to reduce the amount of data in these frames, because it doesn't take a whole lot of data to overwhelm the system. And part of it is, I guess, ROS2 is friendly about that kind of thing. So really the consumption of the frames, at least in my system, was from my HTML page, which, if you recall, in this other block diagram, I'm actually making use of this ROS web video server node for that. So what that really is, it's subscribing and getting the actual ROS image, but then it's making use of an HTML server and serving that as a motion JPEG frame. So we got compression going on. At this point, I didn't enable any compression coming from this vision node, but this ROS web video server can. In fact, you can actually enable H.264, but I found motion JPEG was sufficient. But if I were to have gone in and tried to subscribe to the actual, camera feed, you would definitely have more of a challenge, being that that's not compressed, and that would have been, blowing over the network, the Wi-Fi network. So
Scott,
it is tricky.
Scott, what computers does ElsaBot have on her?
So ElsaBot has 2 Raspberry Pi 4 computers. and each has their own Wi-Fi interface.
Right, if you came late, it's the blue and the green section there are both Raspberry Pis A and B.
That's right. That's right.
Oh,
Yeah.
thank you.
Okay. So that, okay, I'm actually kind of going longer than I probably thought it would take. So that's the vision, or more of the vision. And I think this is kind of a lot of the key special sauce, because I think that's where a lot of people are wanting to play these days. And so hopefully this gives you a good idea of at least, that level of handling. And I think I've gone down to the create, and there's just another function or two in here. Let's see, that the publish function. So there's not a whole lot of magic, just raw message publishing. So
How much of this code did you actually have to write, or how much did you grab from someplace else?
So this is one of those types of projects where at some point it's not real clear how much of this was yours and how much of it was example code, because the Luxonis folks did a pretty good job of providing a lot of different samples. And so a lot of it was pretty much of, okay, here's an example that sets up, let's say, a mobile net pipeline. Okay, I'm going to take the essence of that, but then because I also want to feed it into this, pose detection, human pose, I need to do things a little different, and it gets a little tricky sometimes of, okay, I need this resolution for this, but this one for that. Which do I start with? Do I take one and then rescale it? And if you took one of these paths as depicted in this pipeline diagram, it's really easy. There's a sample, I'm pretty sure there's a sample for all of this, right? The top portion, you can't see my pointer, but I'm pointing to that top half in the blue. That's pretty straightforward stuff. And then if you just do the lower part, that's pretty straightforward. But sometimes when you start marrying these things up, it gets a little bit more tricky, but they're all mostly separable. And it's just, it's not, if you get into it and start to understand how each of these types of pipelines are set up, you can go pretty quick after that and understand how to tweak things. They've done a good job, and I think their documentation is even better now than it was when probably Jim and I both started playing with this stuff earlier in the year.
Yeah, I haven't looked at the docs lately. It looks like they're already better.
Yeah, more samples, and samples are key. And then of course there's more examples, and I wouldn't call my stuff a poster child for the best way of doing anything, but I mean, it works, and it's just another data point to compare, but if you start with the samples, you can make this stuff go. It's not really that hard to do.
Which version of ROS are you using?
So that's a good question. So at the time of the project, I was using a rolling release taken from around April, because I was having an issue with Foxy that was causing the navigation to hang. It was a really low level bug that had not been released, the fix had not been released yet. And it was basically a mutex type deadlock, and so, I ended up, that was a hair puller right there. So finally I just switched to rolling and used that all the way through the rest of this project. And then I switched to Galactic a bit after I'd finished this, and more in the middle of summer. And then now that I'm playing with some other stuff, at least a month or so ago, I found that I was in another one of those binds where certain things really hadn't been carried forward all the way to Galactic, but they were unrolling. And it's that I found that is the most frustrating portion, especially if you're trying to do ROS2 stuff. You can be in areas where you've got 1 foot on the dock and 1 foot on the boat, and it's just, it's just kind of crazy. But if you're sticking with older stuff, I'm sure the life is great, but what pushed me to ROS2 was the fact that I wanted to use Python 3. And, it's been that Python kink, I think, that has really kind of made things painful, because I probably would have stuck with some older stuff maybe if it weren't for that. But it's life. It forces you to work a little harder, I guess, and learn a little bit more. I mean, to be honest, I found that if you're not having a problem, having to solve something, you're probably not learning as much as you could. So you have to kind of look at some of these challenges as kind of a blessing as you go down the road. So let's see.
Hey, Scott,
Yeah.
I just posted your team grand play report, right? I think I got it right there in the chat.
Okay. Well, I was going to provide the slides if you wanted them. So let me kind of bop back over there. Let's see. Let me get this. Oops. this thing going again here. In this slide right here, you've got pretty much everything you'd ever need. And so I can make this little slide deck available if you want it. But let's see if there's anything. I'm not sure how much more time you want to spend on this, but you know, the links on this page do kind of point out more things. You know, the next subject that I was going to talk about, may not have time for, is the behavior tree portion. And the document, I think, does a fairly decent job of that. And so let's
Oh
see.
yeah, you could go, I mean, you could go ahead. I mean, we could reserve the rest of this meeting for you. It's behavior tree stuff is really,
Okay.
people will really like that.
Okay. Okay. I didn't want to run too far, you know, into your other portion of your program. So let's talk about that a little bit then. And let's see, let me get out of this. Actually, it seems like I do this. I'm not sure how to resize these presentations, but this gives me a little more control here. Let's see, go back
Say,
over.
Scott, just to be clear, you're going to post that slide on one of these, on the RSSC mailing list, or?
I can, and I
Okay.
can also put the slide deck up in my GitHub for the top level
Cool.
project. So you'll only need one link and you can get to everything if you can do that as well. And so,
Yeah, that'd be great.
So back to this top level diagram, we're showing the behavior tree node. So as I mentioned, this implementation, which is used by ROS2, is the behavior tree CPP, and that is actually, oops, I've got a link to that right here. And so, you know, if you're going to if you're going to use it, you need to go to that website, and you need to go through this. It's kind of a different way of thinking. If you're not familiar with behavior trees, it's different from creating state machines. And I'll say firsthand, wouldn't call myself an expert with it, but I can make things go, which is kind of the first step of getting there. And I'm sure that that's very familiar with this stuff and look at some of my behavior trees, especially the one for the whole game, and say, wow, what a mess. You know, just like beginning programming is, a lot of times, you know, you can create some pretty gnarly stuff that can be a lot simpler sometimes once you become a little bit, you know, more well-versed. But the gist of it is, it's pretty neat, and it actually allows you to do some pretty powerful things. So there's that, you know, it's kind of a reference, which you need as kind of a starting point. But then what I found was this project was called BT ROS2, and there really wasn't much to it, to be honest. It was a pretty much a very small, you know, project, but I think it had been done by somebody for their particular robot, and it had some basic elements. So it was enough to start, and I'll kind of show you the code. It's this main, let's see, I must have closed that. Let's see. So in the ElsaBot BT repository, there is, let me close the trees up. So BT ROS2 CPP, which it's the top level, it's the one that creates the node and initializes all of the factories that are used to create the different custom nodes. So let me just kind of start here. So here's the main, and it's doing the normal kind of node setup stuff. And one of the parameters is the particular XML file that you want to actually process. And so, and we'll talk about that in just a second. And then if you weren't creating any custom nodes, you wouldn't have any of this stuff here. So basically anything that you want to create as a tree action that's custom, you're going to need to create an implementation, which I'll show you in a minute. And then as far as the initialization, you'll need to tell the behavior tree framework about that, and give it a way that it can create one of those instances with a factory, using a factory, object factory. And that's all this is. It's all boilerplate stuff. It's like once you see how one of these is set up, it's like, okay, I just kind of slap these things in here, and then, you know, I go through, and this is just a more kind of a little more complicated version of the same thing up here, but nothing much different. these are all just different custom nodes that I created for this project. And then if you just see, if you go a little bit further, you'll see where it then actually uses that XML file that was specified to actually create a tree, an internal representation of that, behavior tree. And then at that point, then it's pretty much ready to just start executing that. And it's just a big while loop where it uses that notion of ticking the tree, which is basically going through and processing the tree on each iteration and giving the active nodes a chance to update and process their state. And so this is the high level flow. So you essentially create or set up factories for any of the custom nodes. You load a tree, and then you tell the behavior tree library to execute that. And so that's the very top level. And so if we take an example of one of the node types, and I'm just going to use this human pose detect case. Let me go to the top here. And the gist of this node is that if you recall, the vision node is publishing detections, and these detections are both the human detections, the detections of humans, and also the pose detection. And these detections from the vision node are being published via a ROS message. And so there's a custom behavior tree action node that I created that will subscribe to that human pose message, ROS message that I created. And based on that subscription, it will then make that information available to the tree. So you can actually then determine, well, what is the pose, and tie that into some other behavior. So if we go back over to the code,
now the pose in this case is the robot pose.
Well, this is the human pose. So this is the skeleton, if you say the skeleton, yeah. So this is that information as far as the joint positions, really. Or I guess at this point, it's already been processed down to things like hand on head, touching shoulder. It's that level of human pose info. And so, this, I won't probably go into every little detail here, but the gist of it is that every behavior tree action, there's various types. There's synchronous nodes, there's asynchronous nodes.
Let me back up just a minute, Tim. The behavior tree we're talking about here is the human behavior.
Well, okay, so in this case, the behavior tree is a more generic term. It's really the behavior of the robot. And so the behavior tree is a way to create a description of how the robot should act based on the inputs that it chooses to monitor and react to. And so what the behavior tree notion is, and you're probably familiar with state machines, finite state machines, right?
Yeah.
And where you would say, I'm in this state, and if I see this particular event, then go to this other state. And it gets more complicated than that, but that's the gist of it. Well, that's a way of creating a control structure for a robot or a lot of other things, right? It's a very generic kind of thing, where this is a kind of a different approach. And hopefully this will be a little more concrete in just a second, once I kind of marry this up with a tree. But what you see is, in a nutshell, this particular action, it has inputs and it has outputs. So for this particular action node, it has these strings that say, okay, this is what I'm looking for. So as an action node, I'm wanting to say these are the expected, in this case, left and right pose, and I'm telling you how to check it. And then I want to get out of it what this node has received from the vision node in terms of what is the left pose, what is the right pose. And then if I were to describe it, what text would I use to say that? And so these are the ports, as they call it in this particular framework, input and output. And so when this particular node is ticked, it has a tick function that's called by the overall tree framework. it will actually come in here and it will update its state. And this basically gives this ROS node a chance to spin and receive the latest messages from the other nodes. And then it's going to go in and based on what this node and this function up here, if I scroll up a little bit, this is where the subscriber is implemented. And so if in the case of that update function, it found that a message had come in for this topic head detected pose, then this callback would then have gotten executed, and that message with the left and right pose would have been saved into some member variables, as well as whether or not someone is detected at all, and the number of points that it had found in terms of how, you know, basically the number of joints it had found, just as kind of a qualifier of quality. And so that would get captured, and then this code down here on the tick handler would then look at that and say, okay, well, I'm going to actually just save, you know, this current pose that came in, I'm going to publish that as an output. And same way with whether or not it, you know, a detection was found. This is just kind of a pass through in this case. Oops. And then
It says pose left twice there for right and left.
what's that now?
It's the set output pose left lines of code.
Yeah, that is weird. Let's see.
Looks like the left is double or for both right and left.
Yeah, that is kind of strange. I wonder, you know, we'll have to look at the tree here in a minute. I wonder if oh, you know what? I never use that, because what I also do is I take that left or right and map it to a text string. So it typically, you know, there's several use cases here. So one of them is, tell me what to say. And so if you wanted to say, you know, whether it's left or right, as well as this provides a string that can be compared in the tree. And then there's also a comparison. If you go down further, you can also have this node return whether it was successful or it was a failure, which is the gist of these nodes. You can either be running, or you can declare success, or you can declare failure. Those are the three cases for a node. Yeah. So down here, based on what you tell it as far as expectations, so if you gave it I expect left to be this, like hand above head, and then it goes in and says, okay, if I was given something to expect, then it goes and does a compare to see if that was the pose that was actually found. If so, then it considers the left side good, and then it does the same thing for right. So from a functional standpoint, if you're like the game where it was saying, you know, like put your hand on your head, then at this particular tick, it would have been told, hey, I'm looking for hand on head on left, or, you know, maybe nothing for right. And then, but yeah, that's a bug. Thanks. So this is the, you know, the way the action node is being processed. And if I show you, here's a very simple tree. Well, maybe it doesn't look as simple, but in general, this is a simple tree, and I can run this one too and kind of show you. But the gist of it is, all it does is it comes in and it says, I just repeat this for a whole bunch of times. So it's just going to repeat this sequence, which begins, you know, at this indent point. And then it's also going to use this delay, and then which is, I guess, just a decorator type. Well, I guess in this case, it's not a decorator, but it wraps this particular sequence. So it's going to delay and then execute this sequence. And then in this sequence, it's going to actually use that node that we were just looking at. So that node is called the human pose detect node. And then it's got, as far as the ports, as they're called, it's got this expected pose left, expected pose right, and then an output of what the left speech pose left and what the right pose is. And in this case, I'm not even using those other ports. You know, I'm not really needing those. So what's happening is that each time it loops through here, it ticks this, it uses this node and ticks it, and it doesn't care about what the pose is, because it's, you'll see here in a second, it's really just going to just be outputting it, just tell you what it is. And it does a forced success because normally the success is a function of whether it found an expected left or right. In this case, I'm just wanting to find out what the pose is, if there is any pose detected. So I'm just forcing it to always say good. You'll notice normally for a sequence, it will execute the elements of that sequence until it hits a failure. So in this case, it would always fail because I don't really care about matching. And so it would always just keep, ending here and repeating. And so I'm putting this for success to say, just ignore the output of this and just fill in this pose left speech and pose right speech based on what you find. And so after it executes this, it then says, okay, essentially, if there's, and this is kind of a not kind of thing. It says if pose left speech is empty, so it didn't really see a pose, then invert the result of that so that we don't try to say it. And so, but if pose left speech was not empty, in other words, there was a pose detected, there's a string that describes it, then it actually makes use of a text to speech action client node, another one of those custom nodes to actually say what that text is. So it'll say left and then that particular pose, and then just clears that whiteboard value so that if it doesn't find something the next time, it won't keep saying that over and over. And it does that for the right side too. So I can run that if you want. You can kind of see firsthand how that goes down.
The first part just detected whether there was any, or that first part just detected if there's any pose, and then the second part forwards the speech over to the text to speech action.
Yeah, and this is it seems kind of complicated, but all it's really doing is saying try to detect something, and if you got anything, if the string isn't empty, then say it. Basically, this is really the gist of it. But some of the stuff I have to admit is kind of clunky in that how you have to, at least how I found to have to steer it, to do something simple like this. But there's a whole lot more power elsewhere. So you can't just judge this approach by this one little example, I guess I would say. But here's this particular node running, and let's see if I can. And so, and I have the logging set up. I usually enable the logging on this, and let's see.
So is this running remotely on your Pi?
Yeah. And so I've just SSH'd in, and this is the result. You can see it's like every second this is updating. I don't know if you can even see that, it's kind of small, but let me get the video here too.
You could maximize that, or maybe you can, I don't know.
Yeah, let's see. I haven't been using this particular terminal a lot. Let's see, is it easy? I can, yeah, there we go.
Or just change this.
How's that? Is that better?
That's better.
Okay, don't want fine. And then of course there's that, and then let's see, I think I've got one other. Okay, this is probably more useful here, actually. So all these things going. So let me turn around here.
Onto side, left, onto side, right, onto side, left, onto side, right,
Nice.
hand on head, left, hand touching hip, right, hand on head, right, hand on head, right, hand on head, left, onto side, right, hand on head, left, onto side, right.
So you can kind of get the gist of it. Sitting down, sometimes it doesn't do as well detecting, but that's just a real simple example of, it doesn't really do that much, and that's how I think that's how you build these trees up. You start out with some basic functionality, make sure your action nodes work, test them that way, and then build bigger things. And I'll show you this one, not to go over it, but this is the full game, and there may be some ways to do some includes, but this is it from top to bottom. So let's see, I guess there's 720 or so lines, and this is XML kind of stuff. And so just as an example, here's where it really kind of starts, the main tree. And, and this is, if you wouldn't have seen it from the game, but, there's a mode where if it doesn't see anybody, it just sits there, just kind of watching. And once it detects somebody, it says, hello or whatever. And, so do you want to play a game? So there's a whole sequence of mini prompting to say, do you want to play a game? And you say, yeah. And this is okay. Then how about, and that's where it goes up to another tree, a subtree, and kind of goes through a menu type pick where it's asking, well, do you want to play this or this or this? And then based on that, here's where it's saying, do you want to play robot hide and seek? And, and so it's using a subtree to ask about that. And then if that's successful, then it actually uses a subtree called robot seek, which is where it actually plays the robot seek. So then it goes to that subtree, which is up here. Let's see, which one is that? Here's robot seek. And so that's when it said, hold on while I get ready. Here's an example where, that's where it's saying that. And then, you can see where it's clearing the cost map. And then I created some nodes. Like if you look at the C++, you'll see that, or there's some action nodes that have to do with each game. And so each game, or some of them have a JSON file. So it's a matter of loading that and getting it initialized, getting the state of the game. And so there's some nodes that are specific to that, or to those games. And then, everything you see is all that the game did is all right here. I mean, this is all the magic behavior. And so, if you haven't looked at this stuff, it's maybe worth taking a look at just to see if, you might find it useful in your own projects, because it's definitely an alternative way. And I hadn't really heard of it till sometime earlier this year. And, I think it definitely has some great application in some of these projects.
Yeah, going to ROS 2 might be the best reason or to do that is the behavior trees, one of them.
Well, but you can pull these into any project, really. I mean, it happens.
The best reason to go to ROS 2 is ROS 1 is end of life.
All right, second best then.
Well, to me, it's all about how your project pans out, because unless you're making a product, it's all about your own stuff and what your goals are, right, and what you want to leverage from the ROS community or elsewhere. And so kind of pick and choose your battles, because sometimes it's easier to kind of take it slow if you've got something working in ROS 1. But yeah, you could you could take this library and just link it to your particular node if you aren't using ROS 2, and you could still have all this same functionality.
Oh, I didn't know that.
Oh yeah, it's just another library, C++ library that you just have to get to build and use. So it's pretty straightforward.
Okay. All right.
But yeah, it's pretty cool. So that was kind of mostly what I want to cover. Obviously I could have covered that in a whole lot more detail. There's a lot of stuff going on there, but hopefully that kind of at least gives you an idea. And and if you want to look at this particular code, there's probably better code out there. But if you look at my code and have any questions, everybody's welcome to ask me. To explain. I can definitely explain things a little bit more detail in emails or whatever. So, but just moving forward, the next step. So, like I mentioned, I replaced the 2 Raspberry Pis with a single Celeron based device, and I think I've got about 50% CPU headroom now, and that's with everything running. So because I wanted to be able to run another 1 or 2 cameras, and so I needed to free up some CPU. But this this particular one I chose is kind of nice. Of course, it's quad core, and it's got into M.2 slots, and so it's easy to put in a lot of flash. And then it's got a built-in Arduino, which is kind of handy. And so if you've got some very low level timing a little bit, you want to generate, that's kind of nice. And then the other nice thing I really like about it is because it accepts 12 to 19 volts DC, and it just sort of works with my power arrangement that I have. And I didn't need to do any crazy DC to DC conversion because of that. So it just kind of dropped in, so to speak.
This is very similar to the Latte Panda that I use in my robot, which is also well, it's a Windows machine, but or it could be. It's also the same type of CPU, and then it has a an onboard Arduino.
I bet it's probably the same one. You know how these companies, they I don't know, they tend to end up producing the same thing and putting a different brand on it. In fact, this one is a Windows device. It comes with Windows. And of course, the first thing I do is load Ubuntu on it. So
Yeah,
get it into my world. But yeah, I guess, have you found it to be a pretty decent device? I haven't used it that long, so I don't know if its longevity is there and its reliability, but it seems to be a good fit so far.
yeah, I really enjoy mine. And I forget now if mine, what the processor is. I think it's also Intel quad core. But yeah, it's been great. And maybe I'll have a Linux one someday too, but the Windows, I mean, it's incredible to have a full system that small with all the peripherals, connections. And the Arduino has come in handy too a lot. So
Really?
I'm using that to control my pan tilt of the Oak D, in fact. More, you know, the servos.
Yeah, I ended up using the I guess Adafruit made this one, but it was a 16-channel I2C controlled a servo driver, which is really pretty handy. You know, of course, with that I2C, you can drive that from the Raspberry Pi or you know, even the Celeron side pretty easily. In fact, I guess they have some libraries, Adafruit libraries, that they're device abstraction libraries that they didn't really have support for this particular processor for the Celeron. So I went ahead and added support for that. I have yet to submit that back, but you know,
Hey, Scott,
yeah.
I don't want to get ahead of your next steps, but are you considering something different for a platform based
Yes.
platform?
Yeah. So really my roadmap was, I wanted to get an ARM, like a 5 DOF ARM, which is actually on the robot right now. In fact, let's see if I can, that video is kind of, oh, there it goes. Can you see that okay?
Yes.
So this is actually a little off the shelf ARM, 5 degree of freedom ARM. It's got some of those servos that have feedback position built into them, and that's what I was working on. That's kind of what I've been working on, just not at the same pace as I had been previously on this other stuff, but there is a Ross package for a very similar one that I was taking in trying to get the IK fast solver to work on it, and you know, get it to where you can do something practical with it, and then it can move around and pick up something a little bit more you know, a little bit more complex than my original grabber, which is a really simple thing from the previous project. But the whole goal is that all of this stuff, obviously, if you could stick all this on a different base, and all the rest of this stuff just works, right? So I was thinking of either 6-wheeled or, you know, maybe, you know, one of these, maybe a Rover kind of base or something, or just not really sure, but I definitely am. You know, I can't move this.
How about the DF robot? How about the DF robot like Jim's base?
Yeah, you know, well, actually what I was thinking was more for outdoor, because I thought, you know, it'd be fun to take this outside now and do stuff, maybe, you know, get a GPS module for it and, you know, kind of take it to that level. But yeah, it's definitely something that can handle carpet, because this guy where he is right now, he's dead in the water. If I tried to actually make him move, he wouldn't be able to move. There's too much weight. I've put so much on this.
The bane of our existence.
Yeah, this is, you know, this guy was never designed for the load that he has, and so he does well for what he does, I guess. Especially, I mean, he worked great on wood floor, so which is usually.
Well, it looks like you need to redesign your base more so it can go anywhere.
That's a Create 2, right?
Yeah, yeah. But that's kind of it. That's kind of it. So yeah, so get the ARM on there, and maybe that update the base and create some more games that might be a little bit entertaining, and for my granddaughter or grandson soon, as he's getting a little bit more capable. And so, but yeah, I've had a lot of fun doing this, and it was just neat taking the AI technology, and it was really pretty straightforward to use. And so I encourage anybody that hasn't made the plunge to that level to kind of get their toes into the water and see what you can do with it.
Yeah, Scott. Yeah, I really love what you've done. I was curious. It sounds like you started out the NVIDIA Jetson, and then you moved away from that.
Yeah.
I was curious why you chose to go away from the Jetson. It seems like NVIDIA has a number of software packages that are running Robot ROS2 natively now.
Yeah, well, at the time when I was looking at this about a year ago, it was a real pain because if you wanted to do, you know, Python 3, you were stuck with whatever melodic, I guess, and Ubuntu, what, 1804, whatever. And it was just super painful because if you're going to do any kind of, you know, AI processing, it was just hard to do because of that. And then this OpenCV camera came along, this OD, which then said, well, I don't need a GPU on the SBC anymore. You know, I could use a Raspberry Pi or whatever. Then it just really seemed to simplify it a bit. And, you know, I mean, obviously, you know, NVIDIA's got great stuff going on. There's a lot of stuff. In fact, I used their learning stuff to kind of get, you know, my feet wet and trying to understand some of the stuff. And so, and that is another great path to take, of course. But the fact, though, that this camera also had 3D depth and the processor, the inferencing processor in it, it kind of makes it cool because then you can have more than one camera. And, you know, like I was thinking about putting one on the back, or, you know, it just kind of depends on what you want to do. I mean, there's no real perfect solution, especially with what most of us are doing as far as just sort of hobby stuff. I mean, maybe if you can, you know, swing it, play with both of them, you know, and see which one you like the best.
Do you have one of the new Oak D lights on order? No,
you know, I didn't because I just haven't had as much time to play. And I've got 2 of these Oak Ds anyway. So, you know, to be honest, I don't know why I need an Oak D light. I'm okay with the larger size and all. And
it's
so
lighter.
And so
lighter and smaller.
Well, but you know, at this point right now, you know, I don't think this is my big concern as far as the weight on my project. I've got so many other big things. And so, but yeah, there's a lot of alternatives, you know, in general with this stuff. And, you know, I guess you just kind of have to pick a path and go down it. And, you know, like if it's a Jetson, you know, go down that path and, you know, get everything you can out of
and
that.
And we don't have the light in hand yet.
When are they shipping?
They're supposed to ship it by the end of the year, and they're forthcoming from what I understand, but they're still forthcoming.
Okay. Yeah, I didn't understand there to be that much difference other than more compact, right? Is there really that much more functionality?
Well, small is a big deal.
Yeah, I know there's certain applications where if you just want mostly that as your
big carpet.
yeah. So
okay. Yeah, I don't know. It's updated hardware, obviously, but I don't. I think the specs were a little different, or maybe a slightly improved. But I can't quite remember. You have to look it up.
Yeah, I'm sure they'll have something even newer soon. That'll probably be next generation stuff, which, you know, all this stuff just keeps getting better and better. And, you know, being able to, I mean, I would like to be able to process more, do more complicated neural nets. That's the thing, you know, like full YOLO V4 or something like that. That's what's really needed, because I played around with that, I think, on the Jetson at one point before switching. And it seemed like that was, you know, that solved a lot of problems. That improved the detection capabilities. It seemed like in some of my experiments by quite a bit. But
did you get very far with the Jetson before you gave up with it, or?
Well, I mean, I had used it in that project I mentioned earlier, where is the ball picker project that worked. You know, I was able to actually use their tutorials to train it to detect the little balls I was using, just small little yellow balls. And so I went through and took a number of frames and went through the training algorithm, and it worked pretty good. You know, it's about as good as you're going to get without getting thousands of images. And I think I've learned from that exercise that, you know, your best bet in probably a lot of cases is to find an off-the-shelf neural net that pretty much can do what you need it to do and just use that, because otherwise it's a beast trying to train these things to do something that you really, you know, that you have that's unique, that's super unique. Now, I don't know, maybe Jim, maybe you have a better handle on that, but that's just kind of been my take. You know, that's let the data scientists and the guys that have all the wealth of images train these things, you know.
Yeah, that's a point. I have played with my you know, JetBot, NVIDIA Nano JetBot a little bit, but I haven't done too much. And the training seems tedious, taking all these pictures. And then now Dr. Bruce, he got his to work quite well. I've only done it once, took 100 pictures, and then the thing was bumping around, and I'm like, I guess you know, this may take a little practice to figure out how to take the pictures.
100 isn't enough for sure.
What's that?
That 100 isn't nearly enough, I don't think.
No.
So if you have to take 1,000, well, I mean, to do something really simple,
Yeah.
demonstration, but yeah, it's tedious though, right? And I really enjoy using the neural nets that are out there.
Well, the trick is to use some predefined set that's already out there.
Oh yeah, of course. That would be ideal.
But a lot of these, but if it's a predefined set of images, then it's probably a common image that one of the off-the-shelf nets probably already has as one of its detection types, which some of them have a very large, you know, list of classes. And so it all depends on how esoteric your detections are going to end up being.
Yeah, like if I want to detect doorknobs, for instance, can I find a data set of doorknobs? Probably not. You think?
Yeah, I'm sure.
You might have to pay at some point, because it seems like maybe some of these might be a little
Some of them are pay. One of the problems is that the data sets are really huge for images. One place I saw their data set was 3 terabytes.
Wow.
Oh yeah. By the way, we're gonna have to. I want to announce the end of the formal meeting, and we will stop the recording, and let anybody go who would like to go, because we're at the past the 7:30 mark, and so
Great presentation, Scott.
Well, thank you. It was my pleasure. Hopefully it helps. Hopefully it fuels somebody else's efforts a little bit and gets them over a hurdle or whatever.
Scott,
Can you post the URL to that video?
Yes. And so, yeah, like I mentioned, this slide deck has all the URLs. So I'll take that, create a PDF of that and post that. Or actually, I'm going to check that into my GitHub. And then if you go to my GitHub for ElsaBot, you'll find it there. How about that? That'll be the Uber, you know, point for everything.
Sounds good.
Okay.
it sounds like you use Linux a lot. Was that a Linux IDE you were showing earlier with the XML code in it?
Yeah, that's just VS Code, which runs pretty much everywhere these days, as far as I know. In fact, you know, I'm kind of new to it. I was old school Eclipse guy for a long time, as far as IDEs go, and kind of latched onto this thing because I like its built-in features, SSH and all that, and it's cool.
Oh yeah, I'm a convert to that to VS Code after I think Alan and then Brian Erickson, told me about it, and it's like its plugins are incredible. You can ROS completely plug in Git, and then C++ and all the IntelliSense, and then there's Platform IO I just started using that for Arduino. So goodbye to Arduino IDE.
Well, yeah, the nice thing nice thing right now is that what I was showing you, this code's actually over on the robot. This is on the processor. So, it has this SSH plugin or whatever you want to call it, where it actually is serving the code from over on that remote device to your laptop or, your host machine.
Years and years of field support. So I got accustomed to doing a lot of development with just a text editor and my utility window, whatever terminal window I had, because every time I'd walk into a customer site, it was always a different setup. and I needed to be able to work on all kinds of code and all kinds of systems. So going with a standard terminal and text editor and then running compilers, I was able to do support across 9 operating systems and about 20 languages.
Oh yeah, there's a lot of people that
It's nice to have features like that, though. I really like the layout there for the XML code. And I haven't
Yeah.
seen Visual Studio stuff before.
Yeah, there's a plugin for just about everything. It seems like it really is amazing how this particular framework is taken off.
Yeah, and Docker, it has a Docker one, I think, too, right? And it's just it's growing and growing, and it's free.
Yeah, it is a bit of a memory hog. So
Yeah,
that is a cost. And in fact, every IDE I've used, it seems like that's the penalty you pay. But it's
IDEs keep growing, and
Yeah.
you know what they say: the code always grows to exceed the size of the memory.
Very true. Very true.
Okay, guys. Well, I got a call in the evening, but thank you very much, Scott. It was really good.
Very
Good to see you,
welcome.
Les.
Thank you.
All right, bye, guys.
yeah. Thanks a lot.
See you later, Lash.
That was great. I mean, I like hearing more of the details, and then now I have reading material too. Yeah, from your project. But yeah, I really want to get my the tracking. I haven't used the tracking, neural networks or the inferencing, and then that model for the tracking objects and including people.
Mhm.
And then turning the robot to keep track of the people. That's a big one that I want to do.
Well, that was some of the, to me, that's the fun stuff. When you start to get to that level and you say, hey, wouldn't it be cool if if the robot will actually turn, and then you realize that it's not that hard because it's just a matter of connecting some dots, right? And, and until you get kind of a critical mass going, those little things aren't trivial, but then they become really easy. And it's the fun part of the robot, kind of giving it a little bit of polish, so to speak, in terms of its behaviors. And so.
Yeah, it really, you end up starting to really enjoy in the last, 10% of all of the work that you did for months.
Yeah, all the frustration, because I mean, there's a I don't know, almost immeasurable amount of kind of hair pulling at times, that makes you wonder why you're doing this stuff when you could just be watching TV.
Oh yeah, there's a lot of that. I go through that pretty much on every project. Yeah, I'm doing. I still don't watch TV.
Contrary to what you say, Scott, robots are hard.
If it's easy, everybody would be doing it.
Yeah, I mean,
Exactly.
Yeah, I mean, you kind of forget after a while what the bar is to get started in this world, and then.
Well, I mean, the thing in your mind, the thing's starting to come alive.
Well, it's funny.
Huh?
It's funny how people.
It's actually getting easier and easier, but then your what shall you call it? Things that the robot does becomes more and more complicated because mapping and navigating used to become a PhD thing. Now high school kids are doing it.
Yeah, exactly. But the problem too, it also is the fact that because this stuff is open source, you do have those cases where there's some road, some bumps in the road due to things that crop up in let's say the ROS distributions or whatever that can cause you some pain, some incompatibilities that. And to me, those are the most frustrating because for those, sometimes you actually have to dig into the code and figure out, well, what's going on here and start looking.
Yeah, why is it going off to left field somewhere?
Yeah, and like, okay, was there some recent change? And oh yeah, there was. Oh, look at that. Somebody has, there's some work going on here that's kind of.
Somebody upgraded something and forgot to tell you what they upgraded, and it's sort of interfering with what you're doing because now it runs a little different.
Yeah.
Or it never works. I hit that with actually OAK code too, because that was an ongoing project. And at some point I'm like, I had to go to the latest, the latest branch of their code or what you called it for ROS. It was like what did you call that? The latest.
Rolling. Yeah.
The rolling. So the equivalent of rolling on the OAK. And then I saw there was a fix for the thing that I want. I mean, it's like, you'd be surprised. You think, I'm just going to use the general purpose stuff. I'll never hit their, bleeding edge. And then
Surprise.
Yeah.
Can I do a quick demo?
Oh, yeah, it's open forum now. If the crowd doesn't boo you off, you're good.
Boo, but that's just rhetorical.
So I just mapped this little room here.
Oh,
And
wow.
I'll do some waypoint navigation.
Now, is that your ledgering room?
This is the robot room, as it were.
Oh,
And
okay.
I go into waypoint mode here, and I'll do the floorbot challenge where you go from one end of the room to the other and back.
You're gonna tell it to go there?
Yeah, I've told it to go to the end of the room and back to the other end of the room, and we'll do it twice just for good measure and start navigation. So this
Oh,
is the
this should be
bot
good.
vac.
This should be good.
This is a Raspberry Pi in the bot vac. There you see the robot actually running. I think you see the robot. Do you see the robot
can't see it.
running physically?
No, we just we see a frozen picture of you, and I think everything's frozen.
Oh, let me change the. There we go.
There
Okay,
it
so
is.
there's the robot.
Yeah, the
You see
other
the robot
picture is
now?
frozen.
Yeah, if
Yeah,
you look in the video, you see the physical robot, and then if you look at the share screen, the
right now
ARG
it's
is
moving.
too. And the robot's basically going from one end of the room to the other and back. No hands. It's autonomous.
Oh, that's sort of cool.
And that's it. That's all I got.
Yeah, it's not a fully fledged robot meeting without a live demo from Camp Peavy, folks.
Thank you very much. I'm here on Tuesdays and Thursdays. Tip your waiters, waitresses. They're working hard for your business. Hey, but we did have a breakthrough in the Ross discussion group last week with Michael Wimble and Ralph Gannock. I have a Python ultrasonic code, and I've done ultrasonics on Arduinos 100 times. I've never done it on Raspberry Pi. And so we got the Python ultrasonic code running on the Raspberry Pi. And with the help of Mike and Ralph, shoehorned it into the sample simple publisher program from ROS 2, which is Hello World. And we displaced the string message, the text message, with a range message, which is the ultrasonic message that has the field of view, the maximum length, the minimum length, and the actual distance measurement. Made what I believe is the only ROS 2 ultrasonic package out there, because God knows I looked for one. It's nowhere.
What, is no one using ultrasonics anymore? And it's
It's just, I think it's ROS 2. And nobody's put together an ultrasonic package. And like I said, it was a good learning experience, because I think that's what a lot of this is about, is getting your sensors and taking that sample publisher package and displaying the text with whatever you got, and building packages that way. But yeah, if you could find an ultrasonic ROS 2 package out there, send me a link. I'm all ears. But we actually managed to put something together. Also, it's interesting because of the now its frame ID is sonar_link, and of course you can define that. And I haven't put it into the URDF, the Universal Robot Description Format, so that it rides on the bot vac. But you're actually getting the cone and the distance measurement and everything in RViz, so it's kind of exciting. My story is the smart table, which is basically a TV tray that can reliably get from one place to another and back again. And my current strategy is kind of like Scott, with 2 Raspberry Pis. One's driving the robot, navigating. The other's got the Pi camera for remote viewing, and 2 ultrasonics, so it doesn't navigate under the bed and under the couch.
Yeah, well, that's a good, I mean, and that would be a ROS system. That'd be a
Well,
good,
it's basically the TurtleBot. I mean, the original TurtleBot form factor.
right. I mean, that's a good goal. I mean, it's been my goal, and using the whole Slam Tech architecture and the
But here's where I'm going, Jim, is I know that the create and the bot vac are a dead end street in terms of 3-inch wheels, okay? Because life has thick carpet, right? And so I'm looking at your DF robot wheels there, you know, and thinking of strapping that on a 14-inch diameter piece of plywood, you know, and home brewing a base, you know, with decent sized wheels, put a 2D LiDAR in there, actually, Oak D light, you know what I'm saying?
I have mine on order. Yeah.
There you go. There you go.
Yeah, keeping the weight down is good. I mean, yeah, I just looked at the specs for it. It does not have an IMU. And although they say most people didn't bother using the IMU, and the resolution of the mono cameras are only 640 instead of 1280. You know, there's no power jack, but most, you know, so there's a few things, but it's lighter, uses less power, stuff like that.
And in working with Chaz from France in Texas,
In Texas.
we standardized on this IMU here. It's a Wit Motion IMU, and there's a ROS package for this. And we're looking at, again, we talked about it. I get it. If your project's ROS 1 and it ain't broke, don't fix it, right? But to me, the main reason to be in ROS 2 is ROS 1's end of life, okay? And even if your project is ROS 1 at this point in time, feel free to disagree. You really need to be working on converting it to ROS 2. But the point is, this is another interesting project. It's an IMU out there, and I think Chaz has done the research. He's you know, hasn't found an IMU and ROS 2 package, you know, and so this Wit Motion, I'll probably post on the mailing list sometime soon, because we may as well standardize on IMUs and, you know, sensors and stuff like that, and, you know, work together.
Yeah, that's good. That's good. The more in there, the better. The more support driver level.
Sure.
I mean, I just hope, anybody who does one should upload it and share. I know Brian Erickson, he worked on some of the Oak D ROS connection. Actually, yeah, Scott, that's a good question for you, is because the Brian had some problem with the original, or the code that he had found for Oak D to ROS. I guess someone had tried to put together something initially, you know, as a publish, you know, a node, I guess, some sort of, I can't remember the details, but
was it C++ or was it the Python implementation?
I can't remember now. I think, yeah, I can't quite remember. I mean, I know Brian was working in Python for most of his nodes.
The Oak D, you have to plug, if you're running it with a Raspberry Pi, you have to plug it into a powered hub, don't you?
Yeah, even on my board, I have to plug it into a powered hub from the 12-volt supply. But yeah, for Scott, when you wrote your own nodes for the Oak D pretty much, right?
There really, I mean, especially if you use Python, there really isn't much to it, because, you know, you're just setting up a kind of the boilerplate node, Python node, and then you're publishing, you know, after you crunch the images, right, or process the images, you're just publishing detections, just standard, you know, ROS messaging stuff. So yeah, I'm not sure what the issues might have been.
I can't remember. I have to ask him, but yeah.
Well, I do know at one point there was an issue, it seemed like, with the image format. that was really bogging things down. I think it might have been such that their default processing was just requiring too much CPU. I don't think it was being done efficiently. And I think I did encounter something like that. And then I don't recall it. That was almost a year ago now, or
Yeah, it's a
9
while.
months ago. And I've probably forgotten what I did to get over that, but I'm sure all they're saying. I think I noticed they have definitely more support now for ROS and ROS 2, both C++ as well, which at this point, I'm not looking back on that. I'm not going to go down that path for this hobby stuff. If it were like a real product, I'd probably go the C++ route, but not worth it for this fun stuff. So
I ended up having both. I had a C++ node for the depth for my depth obstacle avoidance camera, which I put on the lower part, which was another OPD. That one I had to use C++ because of an older SlamTech API or stack that was in C++, so had to write C++ to I didn't try to do a bridge or anything. It was quicker. It wasn't a lot of effort just to bridge the SlamTech C code with the depth AI C code. But the biggest problem was building the whole OAK-D library stack in C code and getting that. But that's my job and a day job. So I mean, it wasn't too difficult. And now I do have, it's nice to have the C version around in case you need it.
Yeah, I think the C side of it works well until you have to do a whole lot of post-processing, at least from my perspective. If you're just controlling the camera and getting back some fairly simple results of, okay, here's an object that has the detection results in it. Okay, great. If you're ready to consume that, but if you're getting back, these tensors that, basically a set of data that now needs to be transformed into something more specific, and you're needing to do NumPy like kinds of things. It's like tilt. I'm sure there's ways to do it in C++, but that's not an area I've ever embarked on. And I know it's easier just to pop some Python in there and get it done.
Yeah, for that the whole data science route it's almost all Python.
Yeah,
and you really can't beat the those tools you just mentioned. But yeah, if in my case it was a simple, just grab a depth image and publish it, to this other library. So
yeah. If you're dynamic processing, that's okay. You can do OpenCV on that as well, since there's good C libraries for that library.
Hey, Jim.
Yeah.
Would it be all right if I showed off my latest robot before we end off here?
Yeah, go ahead. I'm gonna have to go in a second, by the way, but yeah, again, it's unless they boo you, I'm not in control of this meeting.
All right.
Crowd controlled.
I'm just going to run the video because if I do it in real life, it probably will fall over. It's the biped I did. Can you see the video?
Yeah.
Yes.
Okay, here we go.
Two. I love how it leans so much, just like Chris Albertson said it would or something. And you think it might fall, but it doesn't.
Like Michael Jackson.
Ah.
Yeah, I think I
Yeah,
need
man.
bigger feet.
It's alive.
I'm not getting enough current through to the motors. They brown out occasionally.
Oh, wow.
That thing needs a lot of current. I'm running 10 amps into the motors. It probably needs 20.
Really, that much? That's incredible.
That's awesome, Thomas.
Yeah, it took a few steps and it didn't fall, and I was very happy about it.
That's pretty neat. It is.
Yeah, it's the lower half of Frankenstein.
Now, when will it do a flip? I mean, okay, when is it going to be
There we go.
Atlas or?
Oh yeah, I wasn't.
You know,
Atlas,
motors for that.
yeah.
Those are off-the-shelf servo motors it's running on. It's about that tall, which is about, I don't know, 30 inches, 27 inches tall.
Needs an Elvis head.
That's coming.
Excellent.
Yeah, but I
Our
gotta
plan for total
figure,
world domination is coming together nicely.
gotta figure out a way to put more current through it. It just
More power.
more power. I need the power, Scotty.
What's the spec on those servos?
60 ounce, it's not 60 ounce inches, 60 kilogram centimeters.
Okay. Wow.
Yeah, they're pretty hefty.
Yeah.
They got to run. Guys, thank you. Scott, excellent presentation. Jim, good to see
Thank
you.
you
Thomas,
very much. See you.
Yeah, I'm gonna get going.
Bill.